Hello, welcome. I'm Daniel Kane. I am here to talk about a strongly polynomial algorithm for approximate Forster transforms and its applications to half-space learning. This is joint work with Ilias, Diakonikolas, and Christos, Tzamos. To get us started, the basic premise here is that of normalizing a point set. So for many applications, your algorithm has input a set of points that you somehow need to process. And sometimes these original point sets that you're given are ill-behaved. They can have extreme outliers, they can be very unbalanced. And for many applications, you really want them to be, better behaved in order to do your analysis. And sometimes you could hope that if this is the case, could be some transformation you could perform on these points that preserves the properties that you are interested in, but fixes this bad behavior. A very basic example is that of normalizing the points. You could replace each point by dividing it by its absolute value to ensure that all points are unit norm, which we'll say is in radial position. And this removes outliers in the sense that now no points are bigger than others. However, when you do this, the points can still be very unbalanced. It could be that almost all of the points lie on some low-dimensional subspace with only a few that are very far away from that. Another thing that you could do is you can make your point set isotropic. So most of the time, there should be a linear transformation where if you apply it to all of the points at the same time, you can put the points in isotropic position, i.e. you can make it so that their second moment matrix is proportional to the identity. So, you apply this linear transformation, you get a new point set. And unfortunately, while this ensures that your points are balanced in some sense, there can still be outliers. You can have some points that are much larger than the others. And the idea of a Forster transform is we want to do both of these things at the same time. So first we apply a linear transformation, the same linear transformation to all of our points. We then rescale all of our points to make them unit norm. And the hope is to put these points in radial isotropic position. That is, a bunch of points that are all unit norm and are isotropic. And if we can do this, it is better behaved than either of the two conditions would be alone, as we'll see at the end of the talk. Now, before we get too much into this, we can first ask the question of, is it always possible to do this? And unfortunately, the answer is no. If there's a subspace V where we have a lot of the points lying exactly in that subspace, then no matter what linear transformation A you apply, the transformed points will lie in this subspace AV. And then when you renormalize it, the trace of the points within that subspace will be too large to make it possible for the points to be isotropic. So it's not always possible to find a Forster transform, but very often it is. So Forster proved in 2002 that if you have n more than d many points in general position, then a Forster transform always exists. This was later generalized by Hopkins, Kane, Lovett, and Mahajan in 2020, which says that, in particular, a Forster transform will always exist unless there is a k-dimensional subspace which contains at least a k over d fraction of your points. And note that this condition here is very close to being if and only if. In particular, if there's a k-dimensional subspace that contains strictly more than a k over d fraction of the points, then the obstacle on the previous slide shows that there cannot be a Forster transform. Okay, so Forster transforms exist in fairly broad generality, and we might want to compute them. Unfortunately, computing exact Forster transforms, nobody knows how to do efficiently, because while these existence theorems show that Forster transforms do exist, they don't show, for example, that you can define the entries of the matrix A over a low degree extension field of the field of definition of your points. And so it might not even be feasible to write down the matrix defining an exact Forster transform. Fortunately, for most applications of this, it's enough to find an approximate Forster transform. And by that, we mean we want to find a matrix A so that if we have this transformation, FA of x is AX divided by the norm of AX. Then when we renormalize the points, the second moment matrix won't be exactly proportional to the identity, but it should be close. It should be identity over D times 1 plus or minus epsilon. And note, it should be approximately identity over D, because the fact that these points are all unit norm means that the trace of their moment matrix will always be exactly 1. And so, this is an approximate Forster transform, and it turns out that they have a number of applications. So Forster originally used them as a theoretical tool for bounding the sign rank of matrices. But later on, it was shown in 2020 that you can actually use Forster transforms to come up with relatively efficient solutions to the point location problem, and later to learning half spaces in a way where the sample complexity does not depend on the bit complexities of the input points. Okay, so for these reasons, it would be nice to be able to compute Forster transforms or approximate Forster transforms, and there have been several algorithms in recent years. So there have been some sort of iterative numerical algorithms by Hart and Moitra and by Artstein, Avedon, Kaplan, and Scherer. The authors of this paper showed in 2021 that you can write down an explicit semi-definite program whose solution gives rise to a Forster transform. And, well, these all work. But these algorithms are what are called weakly polynomial timers. So that is, they're numerical algorithms where the number of operations that you need to perform depends polynomially not just on the combinatorial parameters like the dimension and the number of points and this parameter epsilon, but also on the bit complexities of the input points. And this is a little bit annoying. It means that, for example, if your points are given as real number values, these algorithms are not even guaranteed to terminate at all. And so, well, the goal of this talk is to try and develop this paper is to develop a strongly polynomial time, and that's exactly what we do. So we show that there exists an algorithm given a set of x of n points in R to the d that each have bit complexity b and a parameter epsilon bigger than 0. It performs poly dn over epsilon many arithmetic operations, so no dependence on the bit complexity. The bit complexity of these operations is poly dnb over epsilon. And it either returns a matrix that gives you an epsilon approximate Forster transform for these points, or it returns a k-dimensional subspace V that contains at least the k over d fraction of these points. So either it comes up with an approximate Forster transform, or it gives you a certificate that Forster transform probably doesn't exist. Okay, so that's the main theorem. What is the basic idea of our approach? Well, the Forster transform requires that this transformed second moment matrix is equal to the identity over D. So what we're going to do is we're going to come up with an iterative procedure that makes it closer and closer to that goal. And in particular, to track progress, we're going to look at the trace of the square of this moment matrix. And the point is that the trace of the moment matrix is always 1, once again, because your points have unit norm, and therefore the trace of their second moment is always 1. And given that, the minimum possible value of the trace of the square of this matrix should be 1 over d, and that will be obtained if and only if the second moment matrix is identity over d. And so if we can just keep getting closer to that at every step, we'll eventually be close enough that we have our approximate Forster transform. Okay, so how does this work in practice? So we're given a matrix A, and we have this collection of transformed points. What we want to do is we want to find a matrix C such that C times A as your transforming matrix does better than A. And very conveniently, you can think of these points transformed by CA as taking your original point set, transforming with the matrix A, and then applying the transform with C. And so the value of this means that sort of we only really ever need to work with this XA, these transformed points. And we don't somehow need to keep separate track of what were the original points and what was the transformation we applied to them. The second thing is that, well, what happens if our matrix is not close to identity over D? That means there has to be an eigenvalue get, right? This is a positive semi-definite matrix. We can write, the eigenvalues in decreasing order. If they're not all basically the same, there has to be some j such that lambda j is substantially larger than lambda j plus 1. And what this lets us do is it lets us divide our space into these two eigenspaces, V and V perp, where V perp consists of the big eigenvalues, lambda 1 through lambda j, and V consists of the small eigenvalues, lambda j plus 1 through lambda d. And the basic idea is that if we can move some of the mass of the second moment matrix from the VV perp corner to the VV corner, we can move it from one to the other, that will work to sort of equalize the eigenvalues. It will sort of make the bigger eigenvalues smaller and the smaller ones bigger, and that will decrease our potential. So that's sort of our goal. Now, how do we do this? Well, very basically, we want to make the V component of our points bigger. And the obvious way to do that is to just sort of expand things in the V direction. So we can try taking a matrix C that is the identity plus some alpha times the projection matrix onto V. And this is really pretty effective. For each point X, it basically preserves the V and V perp components of that point, but it changes their relative size, making the V component bigger. And given that it really does move mass from V perp onto V in the second moment matrix. And if it just did that, that would be great. We'd be basically done. Unfortunately, this also introduces some cross terms. So beforehand, we had this VV part, the V part, and then there was 0 on these diagonal components because it was an eigendecomposition. But after we apply this transformation, that is no longer necessarily the case. And this produces some cross terms, and they increase this trace of the matrix squared and hurt our improvement on the potential. Fortunately, this effect is not too bad. It's proportional to alpha squared. Okay, but to really understand this, we need to analyze the effect a little bit more carefully. And how big an effect this transformation makes depends on this parameter beta, which is the furthest that any point is from being either exactly in the subspace V or exactly in the subspace V. And the point is that if they're very close to the appropriate subspace, then applying the matrix C doesn't do very much. And if you do the computation carefully, the improvement that you get in our potential is on the order of alpha times beta squared times some polynomial in dn and epsilon. And the cross terms that you get that make things worse are on the order of alpha squared times beta squared. And that means that in order to guarantee that we're making positive progress, we need alpha to be substantially bigger than 1. And doing this, applying this matrix, we can get an improvement on the order of beta squared. Now, that sounds good until you know that beta can be very, very small. I mean, there's almost no lower bound to it. You can maybe extract something by looking at the big complexities of the points, but certainly beta can be exponentially small if these points just happen to be exponentially close to these subspaces. And if that's the case, we will make progress every step, but it might be a negligible amount of progress. And so in this case where beta is very small, we might need to do something. Now, you might think that the extreme case is even worse. What happens if beta is 0 exactly? All the points are either exactly in V or exactly in V perp. In that case, though, it turns out that we're fine, because if you've got lots of points that are exactly in V perp, it will be one of these dense subspaces that contains too many points, and in fact will give us the certification that a Forster transform does not exist. Okay, but backing off, suppose that we're in the extreme case where beta is very, very small, but not 0. In order to make substantial progress, we need to blow things up by a lot. But the problem is that if we just naively blow them up around V perp, we'll create lots of cross terms, and that will quickly swamp any improvement that we're making. And so to do this, we need to be very careful about where we blow. And the way we're going to do this, we're going to reparameterize things a little bit. We're going to let xb be the set of points that are close to V perp. All the points are close to V or V perp. These are the ones close to V perp. We're going to let U perp be the space of the largest eigenvalues, not of the full second moment matrix, but just the second moment matrix of these big points. And the idea is that U perp, these big points will be basically balanced around U perp. And that will prevent the creation of cross terms. And okay, so that's the plan. As a quick example, we've got this set of points. If we blew up around V perp, the points that we have that are sort of just to the right of V perp on this picture, they would be expanded out way to the right. That would create lots of cross terms, and that would be a problem. So instead, what we're going to do is we're going to create this new space U perp that sort of goes right through the middle of those big points. And then when we expand around U perp, there are actually much fewer cross terms because things are sort of symmetric about U perp when we expand. And more rigorously, so we're going to rescale by a matrix C, which is identity plus alpha times the projection onto U, where alpha is now on the order of 1 over beta. Now, since U and V are, it's not hard to show, are very, very close to each other, this does move mass off of V perp and onto V, and the size of this beneficial effect is on the order of alpha beta, which is on the order of 1, which is great. On the other hand, we can show that this really doesn't create too many cross terms. And the point is that if you look at just the big points, if you write them in sort of the U perp basis, they have no, their second moment matrix had no U perp component because those were eigenspaces of that second moment matrix. If you apply C, which just blows up the U component, that still leaves you with points whose second moment matrix has no cross terms. Then when you renormalize, that might create some cross terms, but you can show that those aren't too bad. On the other hand, when you apply C to the small points were already very, very close to being in U. And then when you apply C, which blows up their U part, they're now super close to being in U. And so once again, there are very few cross terms coming from those points. So this gives us the algorithm. So as long as the trace of the square of our second moment matrix is too big, you compute V perp and beta. If beta is 0, you return this dense subspace V perp and you're done. If beta is small, you compute U and U perp. You let C be identity plus a multiple of the projection onto U. If beta is large, you let C be the identity plus a multiple of the projection onto V, and then you replace A by C times A. You keep doing this until the potential is small enough, and then you return it. And the basic point of the analysis is that every step here decreases the trace of this squared matrix by some polynomial in epsilon and n and d. And so the number of iterations that this requires is polynomial only in those parameters. Okay, so that's the basic algorithm. There are actually a couple of technical points that I sort of pushed under the rug here. Firstly, in order to compute U and U perp and V perp, we need to compute an approximate eigendecomposition in strongly polynomial time. And to do this with the guarantees that we needed to create a new analysis of the power iteration method that gave strong relative guarantees. Secondly, another problem you run into if you run this algorithm naively is that it may well be that at every iteration you double the bit complexity of the matrix A. And that becomes a problem because after polynomially many iterations, you end up with these things of exponential bit complexity, which we don't want. And to fix that, we needed what we call a rounding algorithm, which is basically a way where if you have an A with gigantic bit complexity, you can reduce it to a new matrix with much smaller bit complexity that basically very close to preserves the transformed values of all of your bits. Okay, so that's our algorithm. And I'd like to talk to you about one application to that of learning homogeneous half spaces. So this is a very basic problem in learning theory. You've got a bunch of samples x, y, where x comes from some distribution d. And the y values you get by there's some unknown hyperplane, v dot x is 0. And then you paint the things on one side red and the things on the other side blue. And maybe you add some noise. Maybe some of these are randomly color or something, but let's keep it simple for now. And the goal is to learn a hypothesis H such that the probability over a random x coming from this distribution D that h of x disagrees with the true value of y is small. Or maybe another way to think about this is we want to build a classifier where if I gave you a new random point and asked you what's the value of y, you could get the right answer with reasonably high probability. Now, this is one of the best studied problems in machine learning. There are a bunch of algorithms. Perhaps the nicest one comes if you make a slight extra assumption. If you assume that there's a margin, if you assume that none of the points are too close to the dividing hyperplane, so if you assume that for all x, the absolute value of v dot x is bigger than gamma times the norm of x, you can use what's called the perceptron algorithm. It's very efficient, works great, gives you a clean answer. More generally, you can use linear programming to find a hypothesis that's consistent with d over epsilon many random examples. And then you can show a generalization result that says that with high probability, this hypothesis is correct on a roughly a 1 minus epsilon fraction of future examples. Now, the interesting thing that we're going to look at is what if you want a strongly polynomial time algorithm? And in general, it's interesting, if you want a proper learning algorithm, an algorithm that always returns a half space as its hypothesis, this turns out to be equivalent to linear programming. And whether or not there's a strongly polynomial algorithm for linear programming is a major open question. It's one of the big questions about strongly polynomial time algorithms. However, what we show is that using our Forster transform, we can find a strongly polynomial time improper learner, that is one that returns a more general hypothesis. And the idea is that the Forster transformation is very, very convenient for this problem of learning half spaces. Basically because the Forster transform preserves half spaces. First, you apply a linear transformation that, maintains linear things, so it preserves the fact that there's a half space separating the blue points from the red points. And then you rescale points, which doesn't change which side of the half space they're on. After you've done this, the nice thing to note is that once you have a Forster transform, the resulting space has a margin. Because, well, we know that the average value of v dot x squared is 1 over d. And that means that maybe not every point has v dot x large, but at least a 1 over 2d fraction of these points have v dot x more than 1 over 2 root d. And in particular, this means that we can use a modification of the perceptron algorithm by Diakonikolas and Van Paula. And what this basically does is it gives us a classifier where it learns almost all of the points where v dot x satisfies this margin. So of the points where v dot x is bigger than 1 over 2 root d, it gives you the correct answer with a 1 minus epsilon probability. And of the points that are smaller than that, it maybe outputs, I don't know. Okay, so given that, we basically have our algorithm. So you try and compute a Forster transform. If there's a dense subspace, you look at just the points on that subspace, you recursively do your half space learning in this lower dimensional subspace to learn just those points. Otherwise, you apply an approximate Forster transform. You use this Diakonikolas-Van Paula algorithm to learn the high margin points. And in either case, we'll have found a learner that's very good on some reasonable fraction of the points, but on most of the points, it doesn't know. But then you can just repeat this on the unclassified points. And you just, every time you run this, you learn, a good approximation to your half space on something like a 1 over d fraction of points. And so you run it polynomially many times until you've correctly classified almost everything. And so this is an improper learner because it sort of says, it gives you one hypothesis for the first set of points, and then, of the remaining set of points, it gives you maybe a different hypothesis and some sort of, decision list of half spaces instead of just a single half space. But given that we have this strongly polynomial approximate Forster transform, this gives us a strongly polynomial time. Anyway, that's all I wanted to say. I hope you enjoyed this talk, and I'll see you at the conference.